right now. All right, you can go ahead now and share your screen. And thanks everyone for the wait, and I'm sorry about this.
My mouse click has stopped working, so let me stop sharing and then. All right, yeah. So thanks everyone, and apologies for the wait. So today we are going to look into natural language processing, and today will be sort of the first few minutes or half an hour or so. I'll go through some of the slides, introduce natural language processing, and then after that we will do some coding or look into the exercises. As usual, if you have questions, please do ask them in the chat, and or when I stop for questions, you can unmute yourself and ask questions. Um, all right. So what is natural language processing? So it's sort of the area of machine learning that's very popular these days and with a lot of applications. And I thought, like, rather than giving you definitions, let's look at um, some of the applications of natural language processing that we see every day. So the first one you all might be very familiar with is chatbots. So ChatGPT, if you haven't used it, I assume almost everyone have used it by this point. Search engines is another example of sort of an application of natural language processing. Machine translation, if you have ever used Google Translate, that's sort of a natural language processing task. And then more broadly, other than search engines, more specific information retrieval. So there are products out there that could help you to answer really complicated questions. And some of them dates back to a very long time ago. So Thomson Reuters has this product called Westlaw, which is around since 1990s or even before that. And it can parse almost all the code proceedings and code decisions and parse through those and find you relevant information. So let me just, I have provided the links, but let's just look into some of these to just get a feel for like what natural language processing what natural language processing products looks like. So that's the legal domain Westlaw product. So if you scroll down, you could see things like they could help you find issue specific cases dating back to a whole lot of like 1803. You can do sort of all sorts of information retrieval with this product. Similarly, this Benchside, this is another Canadian company. They have products based on natural language processing that could parse through all the scientific literature and help you find out or discover new drugs or do pre-clinical trials. So that's another sort of example where natural language processing is used. De-identification. So if you have sort of a document where there is a lot of personal information there, so finding out which parts of the document contains personal information, and then removing that information is sort of de-identification or person identifiable information removal. So you could use NLP to do that. So here is another product that does exactly that. So private AI. I just picked a few sort of simple uh, examples where you could just see the product or sort of the techniques of NLP being used in actual commercial products. And finally, in healthcare and finance, there's a lot of sort of other products that do a lot of NLP tasks. So some of them are like here, let's say this one is in finance. So you could, or maybe let's look at the healthcare one. So NLP in healthcare, you could see here that it could do entity recognitions. So for example, here is a sentence, 40 units of insulin at night. So it sort of identified that 40 units is a dosage, insulin is a drug, and at night is the frequency. So it's a sort of an entity recognition task, which is an NLP task. We will look into this shortly. And then entity linking. So if two things represent the same thing, then you need to sort of link them together. Assertions, relation extraction. So if there is a relation between two things or two entities, you could extract it. De-identification is, as I mentioned previously, you could do question answering, summarization, and data enrichment. So all of these sort of tasks are already out there in product shape. So it just gives you sort of the maturity of NLP out in the real world. Okay, so since this sort of series is about AI and machine learning in general, so we have seen some of the basic techniques of machine learning already. So how can we sort of transform all that we saw, the commercial sort of applications, into simple machine learning tasks? So most of what we do with NLP is falling in two categories. One is either you have a long document and you want to classify it into one class or the other, or the document is comprising of words. And so your task is to classify each individual word in that document. So those are sort of the two main tasks that we solve in NLP. And the third one is word generation. So given some initial document, you want to generate or extend that text further. So those are the three sort of main NLP machine learning tasks that we sort of deal with in sort of NLP problems. Now, just looking at these three a little more sort of in technical terms. So if we think of this, let's first look at the document classification. So it's here. So a document is a sequence of words, right? So each word could be represented by, let's say, X1, X2, up to Xn. So there are n words in your document. So that's the input to your model. And then your classification sort of is the output. So the output Y could represent one of n classes. So whether the email, let's say email is your document comprising of words. So your label could be whether that email is a spam or not spam. So that's your sort of document classification. Now, word classification is the case where you have for each word in your input document. So X1 to Xn is again your input document, but your model, your machine learning model, should produce n outputs. And for each input, there is a corresponding label output. So here we had only one label for the whole document. Here in sequence labeling, we have for each individual input token or word, we have I think one per input token. There's one output. So again, classification, but the labels are sort of per token here. And sometimes, or most of the times in NLP, we are concerned with generating word. So let's say we have the first word in a sequence, X1, and we want the model to produce the next word. So X1 is input. X2 is the output of the model. Then we take this X2 and feed it back to the model, and it produces another output, X3, and so on, until sort of a limit is reached, and at which point we stop producing. So this was document classification. This is sequence labeling. This is sequence modeling or language modeling. And the third one that sort of is used in NLP or machine translation is given an input document. We want to produce an output document. So we are given a document comprising of n words, and we produce another document comprising of m words. So those are sort of, we will look a little deeper into some of this today and in the following NLP tasks or NLP lecture. But that's just sort of the broad level overview of what we do in NLP. If you have any questions, please do ask before I move on to sort of what is involved in a basic NLP sort of model building pipelines. Okay, so in any NLP project, what we need to do is, of course, it's almost common to all machine learning projects, is first you collect some data, and then you do data cleaning to make sure that we have data that's usable and sort of in a clean format so that it have minimal noise and is useful for the task that we are modeling. So there is a question about whether this encoder decoder is like a neural network. So any of these could be a neural network. In the encoder decoder, yes, the dominant approach is a neural network. But all of these currently are sort of the model, which is in purple, is almost always in the current systems a neural network. So yeah, you are right on the question. Okay, so coming back to the NLP steps, data cleaning and normalization is part of the steps to perform. Then we will look into tokenization, and we will look what it is, and it also prepares you more for the very modern NLP sort of techniques. And then we will look into representation. How do we represent a document in the computer? And then we will briefly look into modeling and the evaluation techniques. So the first thing is in the pipeline is data cleaning and sort of normalization. So basically data preparation. And so in data preparation, there are a few steps that we need to take. So let's say we have some document, like some text comprising like this. So it's as you can see, some of it is capitalized, some of it is not. It's not in sort of in a standard format. So normalization is just converting it into one form. So either capitalizing everything or lower casing everything. So that's sort of the normalization step. That's the most simple sort of normalization techniques. There could be sort of other sort of things as well. For example, if you have numbers in your text, like let's say you have some text comprising 85. So instead of having the number 85, you want to remove all the numbers and convert it into text. Or there could be dates and times. You want to sort of normalize them or remove them so that they are sort of in a common format. So that's sort of the normalization step. Then for most NLP tasks, punctuation is not very useful. So things like commas and um, other sort of emojis and things like that um, could be removed. And most of the time, like they uh, specifically in classical NLP, um, they used to be sort of removed. Although punctuation does sort of like is useful for certain tasks. For example, if you are doing, let's say, sentimental analysis where like you're finding out whether the document is sort of a positive review or negative review of certain product, then there maybe the emojis are really useful. But in classical NLP, it was really hard to sort of represent how to represent all these sort of ASCII or not ASCII, but Unicode characters and emojis. So punctuation and all these sort of weird characters were removed. And so that's still sort of the case where punctuation is removed. But as we sort of train more and more complex models, this text pre-processing is not as important anymore. And the third step is stop words removal. So if I have a document containing of like words like is, the, uh, things like that. So these are very common words. So these are called stop words, and they don't sort of convey any meaning other than having like a good syntactic structure to the sentence. So if you are finding out whether a document is very negative or very positive in sentiment, these words might not sort of help you to figure that out. So those are called stop words, and usually these are removed. And this helps us to reduce or sort of like um, minimize the size of the data set. And optionally, even further, once these steps are performed, the final steps in data preparation are stemming. So you might have words like goes, going, um, things like and go. So rather than having like three forms of the word in your whole data set, you just remove these variants of the word and just keep the stem of the word. So instead of having like in a sentence, he goes, you would just say he go. And similarly for going, you just replace it with go. And this reduces sort of your data set or sort of the dimensionality of your data set a little lower. Um, because for each word there could be a whole lot of variants, and so you want to minimize the vocabulary. But this is a bit very restrictive. So stemming is like very naive way to reduce the words. So for example, let's say you have two words like care and caring, right? So if stemming is applied to this, this would become car and this will become car, which is like not very good. They change the meaning of the word. So that's where lemmatization comes into play. So lemmatization is instead of doing like sort of stemming in the naive way, it also sort of finds out what is the core word that's being sort of referred to. So let's say if you have words like better, so if you do stemming, it will become bet. But if you do lemmatization, it may replace it with a semantically closer representation of this word. So it may be like let's say good. So better, faster, something like that could be replaced with just the word good. Um, yeah. So there's question whether we like to explain stemming again. So stemming is if you have variants of the same word. So in here I have the example of goes, going. And there could be other sort of variants. If you have a good example, if anyone has a good example, please type in there. But let's say you have like um, Yeah. So you have like one sentence like he goes, sorry. So you have one sentence, he goes, and then you have another sentence, he is going, right? So after, so this represent um, both of these sentences represent some information that someone is going, right? So in punctuation removal, we will just remove the punctuation. In stop words removal, we will remove this is from it. So he goes, he going. And then once we do stemming, we would have sentences like he go and he go, because these two are like forms of the same word. So the stem of the word is go, and that's where sort of what stemming does. It just gets the stem of the word. In many cases, it works, and that's sort of like when you don't have much computational resources, stemming is the right approach to go. But in some cases, stemming doesn't work. Like for example, in care and caring, it will replace it with car, which is like because stem of this word, these two words is car, right? Like it's CAR is common between them. So here it's like not very efficient. Whereas in lemmatization, it would replace care and caring both with care. So because it's the sort of semantically um, more correct or more appropriate thing to replace with. Okay, so that's about data preparation. In most sort of modern machine learning, these things are not as much emphasized, other than making sure that that we don't have a lot of duplication in the data, and that's about it. Okay, so the stem is like the GCD of two strings. Mathematically, you could save it. Uh, GCD is a greatest common divisor, so basically the common sort of part in the two strings. Yes, so you could say that. Oh, okay, let me clean the. Okay. Okay, so that was so we are done with the sort of data cleaning and normalization step. Let's look at the next step, which is um, tokenization. So if you remember basic machine learning, uh, so if you look at basic machine learning, you have let's say if I recall one of the examples in the previous sort of intro to ML lecture, you would have some features like as input. So features could be like, let's say you are doing diabetes prediction. So your Y is sort of like whether the person has diabetes or not. And the features could be some discrete inputs like their BMI or their age, things like that, right? And these would be represented by some numbers. So like, I don't know, I don't remember what the scale of BMI is, but let's say 25 and age is 25 and some other like RBC count or something, red blood cells count or some other blood sort of number is there. So these are the numbers that are input into the model, and the output is a binary output like yes or no, so 0 or 1. So these are nice sort of numbers, and the output is also a number. So now we are looking into, if you have done computer vision already, so you will have a sort of a picture, and the pixels of that picture would be uh, your inputs to the model, right? And then your Y is some sort of like classification. So that's simple in the tabular data on the left, and in computer vision, it's also sort of one pixel is your input, and each pixel is represented by a number. But in text, text is somewhat sort of like a continuous stream of characters. So let's say you have this sentence like, or this document or string, the cats are the mouse. So how do we sort of do we just take the whole input as one single input? That sort of doesn't make sense because a single document could be really, really long. So we somehow need to find a smaller unit that we can input into any machine learning model, right? So a simple thing you could do is, okay, I see a bunch of white spaces here. So all I would do is, let's say in Python, if I have this is text, so this is my text. So I would just do text dot split, and um, it will give me my sort of like a list, a nice list of the cat, saw the mouse, right? And this is then my sort of input vector. So that's all good and nice. The problem is that some languages don't have spaces. So um, for example, like if you have a language that doesn't contain spaces, I think Chinese and Japanese don't have spaces between the words. So then how do you sort of do this kind of uh, white space sort of division? Do we just then use the whole, like this document could be 1,000 page long. So do we just input that into the model? So that's not going to be possible, right? So the alternate sort of quick answer would be, okay, if there is no space, then use each character as your individual sort of input to the model. So you could just say, okay, just use like the H, E, and I think if this is your text, you could just do list of text, and this will give you like a character list in Python. And you might think that, okay, this solves my problem. The trouble with just characters is that an individual character doesn't, or an individual letter doesn't include enough linguistic information. So um, the model might not be able to learn sort of good information, or sort of good wouldn't be sort of able to get uh, enough information to predict your output. So then the the other problem, that's one side of the story, that the white space languages don't have white space, have to rely on this character-based or letter-based tokenization. Even if you have white space, so if you have like these white spaces, you might have misspellings and words that are very, very rare. So look at this sentence. So there is sort of like misspelling or this sort of here. So then do we consider this as a word, like this whole thing, or not? Similarly, this word, I can't even pronounce it, is is it is going to be very rare, right? And look at this word, like this is a medical term. So if you think of all the possible words that could sort of be formed out of the letters, they could be very, very large. So, and remember that in our sort of machine learning case, what we need to do is to, if we have like, let's say, and words, then that's our vocabulary in the sort of the model. So if we have like 10,000 words, then we would be our vocabulary size, or the dimension of our one hot encoded vector, would be 10,000. But if we include these kind of words, these ones and these ones, then our vocabulary size could be millions and millions long, right? And so then our models would have to be really, really large, and there wouldn't be enough data for each individual word. So an alternative would be to just replace these unknown words with a single word called unknown, like just replace it by a single thing, unknown. And this might reduce the complexity or the size of the vocabulary. But then maybe this word is really important to what we are trying to do. Maybe we are just doing some classification, some disease classification based on text. And maybe this word is really important, but we replaced it with an unknown token or word, UNK. And so there is this dilemma of like, if you go to letter-based sort of thing, then the performance would not be good. And if you replace uncommon words with unknown, then performance would not be good. So modern NLP algorithms or even ChatGPT uses a compromise between letters and complete words. And that's what's called subword tokenization. One specific example of it is called byte pair encoding, which we are going to look at in the next slide. So what they do is, rather than doing letters or only words, they do subword division. So let's look at those. So for describing subword tokenization, I will use this as my data set. So let's say I have some text data set, which contains text comprising of this, what you are seeing, like low, 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 lowest, newer, newer, and wider, wider, and new. So now if I just start with this, then I see that the words in this like white space divided words in this text or in my data set are only these words. I picked this example to make sure that we can all follow the example. Although the text itself doesn't sort of make any sense, but bear with me. We just sort of want to do a simple example. So these are the unique words for my data set. So this is my vocabulary, sort of if I were to use the white space tokenization. So in byte pair encoding or in subword tokenization, what we do is we count how many sort of words we have for each one of the unique word. So for low, we have 5 of them. For lowest, we have 2 of them. For newer, we have 6 of them, and so on. So here I have the word and their counts. So that those are the unique sort of words in the total data set. Now, I will initialize my vocabulary initially with all the letters in my data set. So I would start with the underscore symbol, which signifies the end of a word or a word boundary. And then each of the letters that I have encountered in the data set. So in a large enough data set, this would be all the letters that are sort of possible in the computer representation, right? So that's my initial vocabulary. And now you might be thinking this is just letter-based or character-based sort of tokenization. But that's not the case. So next thing that I need to do is find out what is the most frequent pair of characters. So in here, I can see that ER is repeated 6 times in my data set, and ER here is repeated 3 times in my data set. So this is the highest repetition of a pair of characters in the whole data set. So I will combine them together and then replace these 2 characters by a single token ER. So now in my vocabulary, I have ER is a new token. I will continue this process. So if I continue, can anyone identify any other pair? So I see this O and W is repeated 5 times and O and W is repeated 2 times here. So that would be 7. but I believe there may be um, another one that's larger than 7. So if I look at this EW here, it's 2 times, and this EW is 6 times. So that's 8 times. But also this token, the ER token and underscore is 6 times, and ER token and underscore is 3 times. So that's going to be 9 times, right? So that's the next that I will combine together. So now I have ER and ER appearing at the end of the word. So that's another token that I have. And the next one I believe would be EW because that's repeated 8 times. No, I was wrong. So NE is the next one, which is also repeated 8 times. So NE here is 6 and NE here is 2. So 8 times. And then if we continue this a few times, then we will reach a vocabulary of some size, and we specify a budget um, ahead of time. Let's say, I want a vocabulary of size 20. So here, when I reach a vocabulary of size 20, I stop at that point. So this is the basic sort of like, this is how sort of large language models divide the text into smaller units or tokens so that it can process it. Okay, so let's look at an example of how ChatGPT does this. So you have seen the process, and let's now just, oops, I didn't mean to stop sharing. Okay, so I have provided the link. I will provide the link to the document as well. So if I click here, I go here, and here you can see the tokenization that's performed by ChatGPT. So let's say, hello, how are you? Right? And here you see that hello was one token, because these are really common words. So these are by themselves tokens. But let's say, do they have some example? Yeah, show examples. So many words mapped to one token. So many words mapped to one token, but some don't. So don't is sort of split into two tokens, don and apostrophe and T. And indivisible is also broken down into 2 tokens, indiv and isible. So it's sort of even emojis are sort of divided or represented as tokens. And since they are not as frequent, or the bytes or the letters that they comprise are not as frequent, so they are represented as sequence of individual sort of bytes or tokens. And similarly, numbers are also grouped together as three-digit tokens. So this gives you a little bit of an insight into tokenization, and also in the future, if you want to train something like more modern NLP models, then you can you would know what tokenization or what modern tokenization techniques are. I have a notebook here where you could train your own tokenizers. So I wouldn't go into too much detail here, but if it runs quickly, I would show you that the example that we ran through, if we yeah, if we run the same input through the tokenizer and specify the vocabulary size as 20, you would see that the tokens or the vocabulary that it produces is very similar to what we saw on the slides. So you could look into this and play with it if you want to, but it's not very critical to what we. It's not very critical to an introduction. Like for an introduction, it's good enough to know what tokenization is out there. Okay, so in summary, we looked at white space tokenization, where you could just, if you are starting and doing a simple project, you could use white space as your sort of uh, tokenization strategy, but know that that's not sufficient for all languages and for all tasks, and subword tokenization is what is being used recently. And the most popular subword tokenization is byte pair encoding. Byte pair encoding starts with the letters and then merges together the most frequent byte pairs or letter pairs. Um, word piece does the opposite of word piece is another subword tokenization method, and it does the opposite process. So it starts with all the words instead of all the letters. So it starts with all the words and then breaks them down into further and further smaller pieces. So that's a summary of tokenization. Next step is how do we have split the text into smaller sort of pieces. Now what we do with it. So the next step is sort of representation. How do we now we have divided a whole long sequence of characters into smaller units called tokens. Now, how do we represent those tokens using numbers? So that's what we are sort of going to look into next. Any questions so far before I move on to representation? Okay. Okay. So let's look into document representation. So now let's say we have now instead of like that very monotonic string of text, let's say we have documents that are like this. So I have 3 documents in my data set. The first one consists of this text, the cat sat on the mat. The dog saw the cat and the dog barked. So this is my data set. And now I want to do some sort of like, the first thing that I want to do is some sort of tokenization. Um, so let's assume that I did some complicated subword tokenization, but for simplicity, let's just say like that resulted in white space sort of tokenization. So we have tokenized document, and here are sort of the documents after tokenization. So each document consists of these tokens, the Kate said on the map. Now, what is the vocabulary that we have? So the vocabulary is the unique words or the unique tokens in our data set. So that's here, just a few words. And now a naive way to represent the document is to just say, okay, I have the vocabulary. So I would assign number 1 to the, number 2 to Kate, and so on. So just do integer labeling, right? Like just like you would do with any sort of like categorical variable, take the vocabulary as a categorical variable, or and do a labeling of 1, 2, 3, 4, 5, and so on. So this then if you have this sentence or this document, the cat said on the mat, you could represent it as 1, 2, 3, 4, 1, 5. So that's sort of the computer or the feature representation of this this document. The problem with this is that we have assigned the and Kate 1 and 2. So this means like somehow we are signaling that the is closer to Kate, and um, since the is 1 and set is 3, so we are somehow signaling to the model that the is closer to Kate and the is far from this other word called set, which we don't have any sort of like information on, because we don't know which word is closer to which other word. So we are misguiding the model. So if we cannot use integer labeling, what other option do we have? We have already sort of discussed this. Like, there are two ways to convert or represent a variable, a categorical variable in machine learning. One is integer labeling, and the other one is one-hot encoding, right? Like, you could represent each of these with one-hot encoded vector. So one-hot encoding would be when I have the word the, it would be represented by sort of a 1 in the first location, and assuming that this is sort of the index of each of the words. So the Kate, it, on. So this is this, and then that dog, saw, and bird, right? So now to represent this document, we have already sort of presented the vector for the, and then for Kate, we would have this one hot encoded vector, and for set, we would have the third one on, and then we have the again, so we have one in here, and then the main, so we have one in here. So this is the sort of the simplest one hot encoded representation of this document. Okay, so now it's all good so far. But the trouble is that we have this one document, the Kate said on the Mac, and we had another document. If you remember, we had three documents. One was this one, and this one. And if you realize, what we have here is a document consisting of 5 words or 6 words, and the other document that we have is consisting of 3 words, and if I represent them as one hot encoded, I would have these vectors. So in machine learning, usually what you would do is just concatenate the input together, and so that would be your input feature vector. But NLP is different, because now here you see one document is of one length and the other document is of a different length. So how can we solve this problem where the document lengths are different, each input is of different length, but we need to come up with a representation that's of fixed length. So to do that, any ideas how can we combine these representations so that they result in a constant or sort of like fixed size representation? So the most naive way I could think of is just add them together. So I would just add these vectors together, and this would be my representation for this document, and this would be a fixed size, and the size would be the vocabulary size. So I wouldn't have to worry about how many words the document consists of. It would just result me a 1 by v dimensional vector. Yeah, so the one of the answer is to use a neural network, but even to use a neural network, how would we use a neural network if it is of different like we have different number of inputs, right? So unless we sort of discuss that there are neural networks that takes inputs of different dimensions, until then, if we were not having that sort of like neural network available to us, and if we were only going to use, let's say, logistic regression, then how would we sort of represent this document, right? Because this document representation is not only important for neural network-based machine learning. But in general, in NLP, you need to represent the documents, right? Like you might want to do a search engine query with it, or you might want to do information retrieval or all other sorts of things. So you need a fixed size representation for the documents to do all sorts of like modeling techniques, or to use all sorts of modeling techniques. So just like we added the vectors for these words, we'll add the vectors for this other document, and it will also result in a fixed dimensional output vector. Now, if you sort of realize how when we add these together, we get something like 2 in here, and maybe 1, 1, 1, 1, 1 in here, and 1 in here, and then zeros. So if you look at this, it's just the number of counts of each word, right? So that's the counts of each word is represented in here. And that's what gives this representation its name. So this is called the bag of words representation. So it just counts the number of occurrences of each vocabulary item in the document. So in our example document, we have 2 of the word the, and one of these others, and then zeros of these others. So it's called a bag of words because the sequence of words is lost in here. So we no longer have the information that the was preceding Kate and so on. We are just combining it into a bag. Okay. So we can live with the simplification that, okay, it's a bag of words. So the sequence is no longer available to us, or the ordering of the words is no longer available to us. But there are other problems with this bag of word representation as well. So let's assume we have 2 documents, mouse. Let's say someone say, like, let's say this is a transcript of something, and you want to classify whether this message or tweet or email or text message belongs to infestation in the house, right? So document A consists of mouse. Kate chased the mouse on the mail, right? So this document comprises mouse 2 times. And then the second document says the Kate said on the mail, right? And if you look at the bag of words representation of these documents, so document A has this representation, and document B has this representation. Now, clearly, this the is not very important for our document because it's present in both the documents, and it's not like it. If we were to differentiate between document A and document B, the is not very informative. Whereas mouse is very informative because it's repeated 2 times in document A, and it's repeated 0 times in document B. So if a word is present in all the documents, then it doesn't have very much discriminatory sort of advantage. And so it's not very useful, like if it is present or absent in a document, or like whether we include it in our machine learning model or not. So that's where we need to weight the counts with something called inverse document frequency. So you don't need to sort of dive deeper into the equations, but on a conceptual level, term frequency is just the count or the normalized counts of each of the token in the document. And then inverse document frequency is the normalized value of like how many documents contains this word. So if a word is present in only 1 document out of all the documents, then it's highly sort of informative. But if it is present in all the documents, then it's not. And so that's where the count is multiplied by the inverse document frequency. So if we just calculate the same formulas, using the same formulas, if we calculate the inverse document frequency and multiply with each of these token, we get this representation. So in here, since mouse is present only in document A, and the inverse document frequency is log of, let me just do that. So log of number of documents, number of total documents. So total documents divided by the number of documents containing the term. So containing the term. So in here, there are 2 documents divided by 1. Mouse is present only in 1 document. Log of that is something like 1.7 or something. And since it's repeated 2 times, multiplied by 1.67 is about 3.39. So that gives you sort of an indication that, okay, if a document contains a word that's only present in only a few documents, then that's very informative, and that's where sort of TF-IDF is a very common representation of NLP. So if you ever sort of do NLP work, it's a must that sort of you come across the terminology of term frequency and inverse document frequency. Okay, any questions so far? Let me check what's next. Okay. So we now have we now have TF-IDF, which is the sort of the representation of a document. But let's go back to the beginning. So we had this integer labeling. We said the is represented by 1, cat is represented by 2, and so on. But we assigned them manually, right? These 1, 2, 3, and we had no justification that why the and cat should be 1 and 2. And if anything, cat and dog are like 2 animals, so the words for 2 animals should be close together, like 2 and 6. Maybe it should be 2 and 3. But that gets us into sort of a longer argument as to like, okay, how do we decide these numbers? So that was the difficulty with integer labeling, right? And that's why we went towards representing each token by one hot encoded vectors. But can we use neural networks to sort of or machine learning? Sorry about just saying the word neural network, because it's neural networks are so sort of dominant in machine learning that whenever we sort of think of learning, it's neural network. But in general, can we use learning to learn these integer labels for each of the word based on the data set, right? So rather than hard coding it to 1 and 2 and so on, can we use somehow machine learning to learn these numbers for us? And that's basically the very core idea of a very important topic in sort of NLP is learned word representations. So rather than doing sort of one hot encoding and TF-IDF, can we do these sort of integer labeling, but these integers being learned automatically? And as you notice, I have put these integers into sort of lists. So there is no restriction on this being a single number. It could be a vector of numbers, since we are learning them anyways. So if we have a list of numbers, then it would be sort of a more rich representation of each of the token. Okay, so given that, so now that we sort of want to learn the labels for each of the word or token, how do we learn them? So there's a key observation, which is similar words occur close together. So if you have sort of this is sort of a postulate or sort of a theorem in computational linguistics, is that if two words are similar, they will occur close together. So exploiting this idea, researchers used uh, sort of a machine learning model to predict, given a word, predict its close by words. Like given, let's say, is there an example coming in? Yeah. So here, since we had the cat is the cat set on the map. So given the word cat, can we predict what words would occur closer to the cat? So we define a model or sort of use a model to predict that the closest words in our data set with cat are the and set. And close by is defined by a certain window. So let's say predict the words that are within 2 words of the given word. So when I say a window, so if let's say you have the cat set on the map. So if my window size is 1, so that means 1 word to the left and 1 word to the right is considered close by. So for set, it would be this word and this word. So the prediction would be to predict this and so on. So that's one way to sort of model this thing. So now, given this, you have the inputs, you have the targets, so you can use any of your favorite machine learning model to do this prediction. Okay, so that's one sort of way to solve this problem. The other one is the opposite of it. So given the target word, given the surrounding words, so given the and set, can you predict what was here? Can you predict Kate, right? So that's what continuous bag of words model do. Given the surrounding words, can you predict the target word? So these are the two dominant sort of models for representing words in NLP. Okay, so let's construct this. If we have this data set, let's construct and let's say our window size or context size is 1. Let's construct the data set for this. So if I go through each of the word, I would see that within a one window like a context size of 1, I would have for dog predict the or predict saw or predict bark, because if you see here, dog is um, having a neighbor of the and a neighbor of sa, and similarly it has a neighbor of the and neighbor of bark. So for your neural network or any other machine learning model, your input would be the target word, the dog, and then the predictions would be one of these. So these are sort of one example is this one example in your input is this one, and one example is this one. And then use any of the cost functions to predict the correct word. Okay, so in practice, how this is done is you construct these data sets, and then what you do is you somehow have to you use a model, right? So in the original word2vec model, what they did was just did matrix multiplication. So this vector is of size v, which is your vocabulary size, and you initialize a matrix, which is of size v times d, or d times v, and then you initialize another matrix, which is d times v. And so the input is a vector of size vocabulary. The output is a vector of size vocabulary, but in the middle, you have a smaller dimension, d-dimensional vector. So you train this model on the data set that we provided or discussed on the previous slide. And then once the model is trained, you, of course, you have to have like a softmax function so that it predicts only one output. Like once you pass it to softmax, it produces probabilities, and then you take the maximum of that, and that gives you the probability, the label for the word that has the maximum probability. And once this training is finished, then you scrape off the second part of the model. So you remove this, and then for any given word, you input it through this or multiply it with this matrix, and then it produces an output which is d-dimensional. And that's your sort of the labels, which before we assigned hard-coded labels, right? We said like, okay, cat is number 2, or dog is 6, right? We had these hard-coded numbers. But here, once we do this process, the skipgram model gives us vectors, d by 1 metric, vectors that are learned values. So it could be something like 0.31, 1.1, 0.9, and so on. So this was a very sort of revolutionary moment in 2013 or 14 in NLP. And this sort of representation has some really good properties. So this is just a toy example. It's not realistic, but if I were to do this for the example data set in the 3 sentences that I had, where was my data set? So if I were to do word-to-vec training for this data set, I might find that once I trained with d equal to 2, like 2-dimensional embeddings, and then I plot them, what I might find is something like this, where I have dog represented by minus 0.5 and minus 0.1, and cat closer together. And the is present with almost every word, so it's in the middle. And then dog has barked, so it's closer. And if I had like a couple more sentences, then like mew might be meow, cat would be closer, and something like that. So this gives you a more sort of like a integer labeling, but more learned integer labeling or representation that's learned from the data itself. Okay, so that's word2vec. Let me limit run. Any questions so far? I know it's a lot to cover in a short time, but if you have questions, please do ask them in the chat. Okay, so I just show a simple example, but people did a lot of analysis on this, and there were really good properties of this word-to-vec model. So if you had words like walking and walked, and swimming and swam, they were the words of similar form were closer together, and the words that were sort of not similar were further away from each other. Similarly, if you had countries and their capitals, so there was sort of a constant or parallel distance between those entities. Similarly, you could do arithmetic with words or word representations. So if you add like Monday plus 2 days, or like something like that, like for Monday and Tuesday. So maybe it will give you the vector that's closest to Monday, Tuesday, Wednesday. So it will give you something like that. Some vector, like if you combine the vector for Monday, with the vector for Tuesday, it will give you a vector that's closer to the vector of Wednesday. We'll have another popular example is that king king minus man. So the vector representation of the word king minus the vector representation for man plus the vector representation of woman will give you the vector representation that's very close to the queen. So this was surprising. In hindsight, or sort of now, it's not surprising because it's just a learned representation. But it was very surprising at the time that this kind of relationships exist in the learned representations. Okay. Let's see what I have on the next slide. Okay, so just a summary, and maybe we can take a 5 minute break after this. So in summary, we have looked at one hot word representation. So remember, this is word or token, like token or word representation. And in this, we discussed bag of words. And this bag of words is a document representation. So multiple tokens combined together. So that's bag of words is a document representation. Really important to sort of keep in mind. And then along with bag of words, we discussed TF-IDF, which is also a document representation, right? So this was one hot word representations. And then we looked at word-to-vec word representations. And these are, again, word or token representations. And so this will give you those d-dimensional sort of vector for each of the word. So word-to-vec is not a document representation. You can combine word-to-vec vectors for each of the token to come up with a document representation. Just like instead of in bag of words, you could, rather than using one hot encoded vectors, you could use word-to-vec encoded vectors, and that would be sort of giving you a document representation. So that's all for the representations. One downside of this sort of these representations is these are static. So let's take an example of let's say a sentence saying like I saw a fly, right? And fly is my token or word. So this may map to something like 2, 3, 4, let's say, right? Three-dimensional representation, and the vector that fly maps to using word-to-vec is, or even using using one hot encoding is 2, 3, 4, right? So this will be fixed. So let's say I change my sentence and I say like I can fly a plane, right? Now, this will also, if I find the representation, the word-to-vec representation of this fly, it will be the same because it's just the only input that goes into the word-to-vec representation is one hot encoded vector, like the current word, the identity of the current word. But semantically, as you can see, these two are very different things, and it depends on the context, whether I am referring to an insect or I am referring to sort of a noun, like or a word, fly, that I can fly. So that's the downside of word-to-vec representation, and that's where the next revolution of NLP starts, where we have word representations that are contextual. So it depends on the context what the representation of these words would be, and that's where all the sort of the transformer models or modern sort of techniques comes into play. So we will look into some of that in the next lecture. But today we are just looking at the static representations. Okay. Any questions so far? Okay, so let's take a 5 minutes break. Let me start a 5 minute timer if that's okay with Sebastian. Is that going to be okay if you're still here?
Hi, yes, it's going to be fine.
Okay, so I will leave you with a 5 minute timer and we'll be back by in a few minutes. All right. Okay, so let's get started. Okay. In my slideshow. Okay, so so far we have looked at what did we look at? So we looked at cleaning text and so cleaning we looked at tokenization. Specifically we looked at um, byte pair encoding or subword tokenization. And then we looked at representation. So in representation, two things to remember, or if you are sort of writing your notes, you really need to know what TF-IDF is and what word-to-vec is. And then now that we have the representation, so in the beginning, we had these boxes of like a model, something goes into it, like x1 to xn goes into it, and something comes out of it. So it's y1 to yn, or just a simple 1y. And so now is the time to look into some of the models. Fully, you have built some of the knowledge from the previous lectures as well. But I will explain the ones that I am going to sort of use today. So let's get started with the models. So again, to reiterate, we have a bunch of these different tasks. So sequence labeling, we have fixed size input and inputs. And then we have a corresponding set of outputs. So n outputs. In sequence classification, again, we have n inputs, and then the output is a fixed one output. So n could be varying from one example to the next example, but y is fixed. In sequence modeling, it's more open-ended. So when we stop is not determined deterministically, but it's when we produce or when the output token is a specific word or a specific token. In encoder decoder, again, we have from one example to the next example, the n could be varying, and similarly the output m could be varying. So this begs the question of like, we could use like specifically for sequence labeling, if you have used, let's say, multi-class logistic regression, you could just use logistic regression to input one token and have the corresponding output, another logistic regression to do this sort of one-to-one mapping of each input to an output, but that would be very inefficient, right? Similarly, for sequence classification, it's very common to use random forests or even logistic regression to do document classification. So you could represent these documents using TF-IDF vector or word-to-vec vectors, and then feed them into logistic regression or any other sort of scikit-learn model and produce or predict the y. So those are sort of the simple cases. But what if you have word-to-vec representation that's like increasing with the size of, or have variable size of inputs. So one document might have 10 words and another document might have 13 words. And then how do you deal with it? So that's where a specific type of neural networks comes into play, and they are called recurrent neural networks. So I assume you have already seen some form of neural networks, but if you have not, let me just quickly recap those. Maybe I can do it on an empty slide somewhere. And let me create a new slide. So in a normal neural network, what you would have is you have your sort of inputs coming in, and then you have a bunch of matrix multiplications. So you multiply a matrix with this, and then this produces an output. So once you sort of each one of these represent the rows of this matrix. So W1, W2, W3 is multiplied with the inputs. And similarly for this other output, you have this other W1, W2, W3 multiplied with these. And then you pass them through a sigmoid or some sort of nonlinearity, let's say a rectified linear unit. So if it is less than, let's say, 0, then you set them to 0. And if it is greater than 0, then you pass it through. So that's sort of the simplistic sort of multiply by a weight matrix and then apply this activation function. But so if I were to represent this in equation form, I would have W times X, and this passed through some nonlinearity. And if I have multiple layers of these, I would have another W times the output of the previous layer, and so on. So that's my normal neural network. What we are looking at today is a recurrent neural network. So we would have the same box that I have there. So I have W and some X goes into it. So X1 goes into it, and it is a vector, just like we had this vector here. 1, 2, 3 inputs. So let's say we have some values 1, 2, 3. So this goes into this, and this produces an output, let's say Y, but it also have not just only one matrix, but let's say call this Y, WY, but also WH. And it also produces something called a hidden state. So it also produces an H. And then we take in that same H and goes into the next sort of time step. So the W Y and WH remains the same. Another X comes in. So at this point, we have X2, and it produces a new H and a new Y. So nothing changes in terms of the matrix multiplication, but a little bit of change as to what do we compute as output. So we compute two quantities, not just only one, but two quantities. One is the current output of the layer or the network, and the other one is the hidden state of the network. So to look into this more concretely, or sort of how is this used to model language? Let's say if we were doing language modeling or sequence modeling, what we would have is we would start with some initial hidden state, H, and we will multiply it by WH, the matrix, which corresponds to the hidden state. And we would have some initial input, let's say the word my, and maybe it's one word-to-vec representation. So maybe this is the word-to-vec representation of the word my. So this goes into the network at this current time step. And these two are combined to produce some output, Y1. And then that Y1 is fed back into the same network. So this is taken and input into here, and then it produces the next output. So that's the basic idea of a neural network, and we will sort of implement one of its kind, so you would have a better sense of how it's done in code. But I'm assuming that you have some level of familiarity with Python and PyTorch. Okay, so that's enough for the modeling part. We will look into the code and analyze more there. But before we go to the code, one last slide on evaluations. So in terms of how do you evaluate these how do you evaluate these different tasks that we just discussed? So if it is just document classification, then you evaluate it with any other sort of document classification metrics. So you use F1 score or precision or recall or area under the curve. So that's easy. But if it is a task like language modeling, where like you have the first word as input, my, and then it produces favorite, and then you input favorite, and then it produces color. I don't know what was in the previous slide, but let's say you input the color then next, and it produces is, then this is sort of seems like a good language model. But if I had to input like my favorite, and if I input favorite and it says color, and if I input color and it says, I don't know, some random word like blah. So that would not be a good model, right? Like that wouldn't be a good language model. Um, so how do we measure this? So the way we measure it is after we have sort of input the my favorite color, the next word that it predicts should almost be deterministic. Like should almost have like if any word in this position is possible, like if the probability of, let's say there are 10 words in our language, and if the model assigns equal probability to all of those words, then that's a really bad model. But if it assigns almost one like probability to a single word, and if that word is the sort of one of the possible correct words, then that means that, okay, our language model knows what the next word should be according to the language. So this idea of like having a uniform probability for the next word versus a very opinionated probability for the next word is captured by perplexity. So the higher the perplexity, the bad the model is. The lower the perplexity, or the lower sort of the non-uniformness or skewedness of this distribution, the better is the language model. So that's the language model part. And then we also looked at the encoder-decoder models, where input is a text document and output is also a text document. So since this input, maybe this input is a sentence in French, let's say, and this is a translation of it in English, right? So this translation, how do we evaluate how good this translation is? So what we would have is like a ground truth translation, a ground truth text. So what we need to do is like, this is y predicted text, and this would be the y ground truth text. And so we need some mechanism to compare two pieces of text. And that's where sort of the blue score comes into play. So blue score is how closer two pieces of, it's a similarity between two pieces of text. So it basically measures a closeness between two texts, text one and text two. So we are short on time to describe further, but know that sort of if you are doing sequence to sequence modeling, let's say question answering or machine translation, you want to use this blue score. But sometimes this blue score is more similar to a precision. So how much of the ground truth text have you captured? So if I am translating, let's say from French to English, I don't want to miss anything that was. I don't want to sort of like produce anything that wasn't in the original sort of text, right? But if you are doing text summarization, so if you have like a large body of text, and if your output is very short, let's say a summary of that text, then in that case, you want to use some metric that's recall oriented, so that you can sort of pick everything that's in the ground truth uh, uh, text to be captured more thoroughly. So in that case, you want to use Rouge, which is recall oriented sort of metric. So these are the two things that sort of you need to look further into if you are evaluating NLP models. So now, quickly, I will go through two things, and then we'll sort of, I will leave you with an exercise. So let's do some coding in the notebooks. So first, let me share. Okay, so what we will be looking at is, so hopefully, if you are not familiar with Kaggle, I would highly encourage you to sort of look into Kaggle, and also make an account. And if you are new to this sort of machine learning, which I assume most of you are, Kaggle is a really good way to practice your skills, and maybe build some small projects and put it in your resume, so that helps you to sort of market yourself as a sort of a machine learning engineer or data scientist. There are, if you go to competitions, there are a lot of these simple, not simple, like some of them are like very complex, but you can find the getting started, you can find some of the competitions that can sort of help you to get started quickly and really get up to speed. So we will look at this this one, natural language processing with disaster tweets, and it comes with its own data. So this competition is about you have a text, and then it contains a tweet, and then you need to predict whether that tweet is about a disaster, or like does it say that a disaster happened, like a natural disaster happened, or not. And the idea is to like being able to correctly identify whether a tweet is about some disaster or not. So I was lazy and I didn't do the competition, but you can look at the leaderboard, and you can look who is sort of like leading this. So I think at number one is this person. They submitted 2 months ago, and so on. So if you become good at it, and if we are going to discuss one of the solutions in a few minutes. So if you learn more of NLP, then I encourage you to submit to this, and maybe you will be at the number one. So um, so I highly encourage you to sort of participate in these. So they provide you the code, and also when people submit their code, it's also available to you. So you could use existing notebooks and existing submissions to basically further your sort of understanding, and also make improvements on that notebook, and then resubmit to the competition, so that you can also have an entry. So I'm going to use this submission from here. I just copied that to Google Colab. So here it is. It's the same notebook, and I will just quickly walk you through what is happening in each of the blocks. But before that, let me just run it from end to end. So I obtained some the tweets data from that Kaggle website. You need to log in to get that data, but I've already sort of copied it to Google Drive. Probably not a good thing to do, but anyway, it's for educational purposes, so it's fine. So this is based on this is based on PyTorch. So first some imports here, and then we have two CSV files, train.csv and test.csv. So if we looked at the training data, so we have some ID from the CSVs, and then there is text. So I would be interested in displaying one of the text in full. So let me just do that. Train data. But anyway, you can see that it's forest fire near Canada. So it definitely is indicating that there's a fire somewhere. So this is the train data, and then let me just also do the train labels. Train labels dot head. Is it a frame or since I run all the cells, so I think it's training down there. So it's not going to run for a while. It's training. So anyway, so we have the inputs as these. We will be using this text as our input, and then the target labels is the targets. So as we see, there are a bunch of not a numbers, although we are not using the column, or at least not important for our purposes. But here, not a numbers are replaced with zeros, so hopefully it's familiar. And then here's a function to remove punctuation. So that's the data cleaning part that I mentioned in the slide. So you can use sort of string.punctuation to remove any characters that's not that is a punctuation mark. And if there are HTTP links, then you want to remove those as well. So that's also sort of a data cleaning thing to do. And then you use this function to transform your text and keyword and location sort of columns in the pandas data frame. So here are some of the tweets. So forest fire near says Canada. So it seems like a tweet that's representing a disaster. And then here we are displaying the categories. So the data set is more or less balanced, like not disasters is about 4,500 tweets, and 3,500 are the disaster ones. Here we are building a PyTorch dataset. So PyTorch datasets basically enables you to read each individual tweet at a time, and maybe if there were any transformations needed to be performed, you could do that in the dataset object. So once you have this sort of training dataset, you can use this to get batches of data. So nothing special here, splitting it into training, validation, and test sets. And here is where we are counting how many words or sort of unique words or vocabulary is in our data set. So as I mentioned, in this case, we are using really simple white space tokenization. So we have text.split, and then we are counting how many words do we have. So once we are done with our vocabulary, coming down here, we have a PyTorch LSTM model. So that's very much similar to what I described, the recurrent model. So we have an embedding layer. We have an embedding layer, and then we pass that embedding layer input to the LSTM layer, and then perform some more linear layers on top of that. So here we have the embedding, the LSTM, and then we pass the output through the fully connected layer here. So that's our model. And then the normal training loop of PyTorch. So we iterate over the data set. We set the optimizer to have 0 gradients, do the predictions, do a backward step on the model, and run this training for a bit. Some evaluation of the accuracy, classification accuracy, and once we sort of run the training for a while, we get a validation accuracy of 61.89% and training accuracy of 70%. And then if we do evaluations, we can plot the confusion matrix. So here you see actual negatives versus predicted negatives. So 368 of true negatives and 122 of true positives. But there are false positives and false negatives as well. And some examples that were printed from the predictions. So here is a tweet which was labeled as positive. So the police chief assured the crowd that this officer-related shooting would be investigated. So it seems like it's I don't know if it is a disaster. I was thinking more of like a natural disaster, but it does indicate some sort of like a problem, right? Yeah, screaming. I think the model got this one wrong. And so on. So anyway, this analyze this and play with it. Of course, this uses just white space-based text splitting. So you could try tokenizing with byte pair encoding. Also, this uses just one hot encoding here. So you could use word-to-vec model and improve on this this notebook, and then resubmit to Kaggle and see how does your model performs on the Kaggle hidden data set. So they share some of the data with you, and you can build a model based on their data, but then they evaluate it on a test set that you don't have access to, or anyone don't have access to. So it's a really good way to test out your machine learning skills. All right, so that's it for today. Hopefully you got a sense of what NLP is all about. And in the next lecture, we will look more into more modern NLP techniques and transformers, etc. I'm open to any questions. I think we are almost out of time, but I'm around. If anyone have any questions, please do ask.
Thank you, Dr. Khan, for your presentation. That was great. So we would stay here. If you have any question, you can just write it in the chat.
All right.
So seems like there is no question. Thanks again, everyone, for joining. First of all, we have the next session would be on Sunday evening at 5 p.m. And it would be our last lecture in the second phase of AIR Research School. It would be on more advanced topics in NLP and how to use a pre-trained model and how to fine-tune that. Dr. Khan would join that again. We would really appreciate here for Dr. Khan, and thank you, everyone. So see you on Saturday.
Thank you. Bye now.
Bye.